The method of Lagrange multipliers, I'm trying to say Lagrange in French and multipliers in English, Lagrange multipliers is attributed obviously to Lagrange, but was probably already known to, for example, Euler that preceded him. This is 18th century mathematics. Lagrange is a very important guy. He was actually born Italian as Lagrangia, but I think he had French origins in his family, and he moved to France, and he became a very famous French. He's buried in the Panthéon in Paris, and I don't know if you've been to the Eiffel Tower. Have you been to the Eiffel Tower? So the Eiffel Tower has names of famous French mathematicians and scientists and engineers on it. There are about 70 of them, and he's one of them. So he's a very respectful French mathematician, along with some other famous ones like Laplace and Cauchy and Fourier. And you've seen his footprints all over Calc 1, right? You know the Lagrange theorem, and so here he is again. So what's the theorem? Remember the problem that we're handling. We want to find minima and maxima of a function, what we call the target function, but subject to certain constraints, only for points x, y that satisfy a certain relation, which we called the constraint, and expressed it by a function gxy. So here's the statement of the theorem. The proof of the theorem that I'm going to write is not difficult, and it goes through the implicit function theorem. I'm not sure we're going to see the actual proof. It's less important than the intuition behind it, and that I want to show you. So here's the theorem. So this is the theorem stated for two variables and a single constraint. And we're going to generalize it later for more variables and more constraints. So this is the simplest version. So let fxy, here's the two-variable function, and we're going to assume, as always, that it's C1, continuous partial derivatives. Let x0, y0 be an extremum, a minimum or a maximum, an extremum of f. This is the target function, subject to the constraint gxy equals 0, where g has to be in C1 as well. You've probably noticed by now that every reasonable theorem in discourse assumes C1 on all the functions involved. Okay. Assume further, it looks like a technical condition, but it's important. Assume also that the gradient of g is not 0. So the derivative of g with respect to x could be 0 as long as the derivative of g with respect to y is not. They can't both be 0. That would mean that the gradient of g is 0. And the reason that they can't both be 0 is hidden in using the implicit function theorem to prove this. Okay, that's where you see it play a role. And what does the theorem say? So far we just filled the board with assumptions. Then there exists a number which is usually called lambda. This is the Greek L standing for the French Lagrange written in English. Okay, so this is the Greek L, lambda. There exists a lambda. This is what's called the Lagrange multiplier, lambda, such that, what does lambda satisfy? It's just a number such that the gradient of f plus lambda g at the point vanishes. You take f, it's a two-variable function. You take g multiplied by lambda, it's a two-variable function. You add them, you take the gradient, that's a vector function. You calculate it at the point. You get 0, 0, or the vector 0. Let's write it 0, 0. No, let's leave it like this, because then it's going to be easier to generalize. Is it clear what the statement says? Okay. Now, how do we use a statement like this? Note that this is still a Fermat type of statement. What do I mean by that? In order to find points x0, y0 that are extremum, what do? We calculate this derivative and set it equal to 0. The points that satisfy this are potentially extremal points. Not necessarily. We have to later on classify them, and we're going to see how to do that, but they have the potential of being extremum point, because points that are extremum has to satisfy this. Clear? So it's the same idea. They're not usually called, or maybe they are called critical points, I don't know, but it's the same idea. It's the same idea. Some derivative-ish expression has to be equal at extremum points. Okay? So before we do an example, I want to write how we use the theorem. So instead of writing it in theorem form, write it kind of in a recipe form. How do we use it? And then I want to show the reason why it's true, the geometry. There's very nice, simple geometry behind this, and I want to show that, and then we'll do an example. So first of all, remark, this is not a sufficient condition, only a necessary condition. So setting that gradient expression to be equal to 0 does not guarantee it's an extremal point. It only gives you critical points. And the method, so this clip is called the method of Lagrange multipliers. So how do we use this theorem? We have to go back to this board a second. The method is solving a system of 3 equations. The first equation is g of xy equals 0. That has to be satisfied for the points that we're looking at. X and y have to satisfy this. Do you agree? Okay. But they also have to satisfy 2 more equations, which are hidden here. There are 2 equations here. One says that the derivative of f plus lambda g with respect to x equals 0. And the other says that the derivative of f plus lambda g with respect to y equals 0. Do you agree? Okay, there are 2 equations hidden here. The gradient is 2 functions written as a vector. Okay, so the method is find xy that satisfy this system of equations. Fx plus lambda plus lambda gx equals 0. Fy plus lambda gy equals 0. Maybe I should emphasize, oh, never mind. And g of xy equals 0. Okay, and how many equations do you see here? Duh, 3. How many variables do you see here? Y? 3. What's the third one? Lambda. Okay, lambda is an unknown as well. And we will see in examples that as we solve this, we actually don't care about what lambda is. We want the x and the y, right? But sometimes it's easier to find lambda along the way and use that to find x and y. But we're looking for x and y's that solve this system of 3 equations and 3 variables. So this is 3 equations in 3 variables x, y, and lambda. Good? So that's the method. We'll do examples in a minute. Okay, I want to explain the geometric intuition behind this theorem. So geometric intuition. It's not a formal proof, but it's the idea. It's the idea. So what you should have in mind is the example that I gave previously of walking on a trail, hiking on a trail along some terrain, some mountain range or hills or whatever, okay? And what you're looking for is the highest elevation which you reach on that trail. That's not necessarily the highest elevation of the mountain range. It's only the highest point the trail reaches, okay? So here's a bird's eye view of a topographic map, okay? So here's the level curves which present the topography or the elevation. Okay, so suppose the elevation looks something like this. Here's one level curve, here's another, and here's another, and here's another. Okay, these are the level curves. Okay, so let's say at this here the height is 100 meters, and here the height is 200 meters, and here it's 300 meters, and here it's 400 meters. It's a bird's eye view, and these are the level curves. Is it clear what I'm drawing? Okay. Now let's take a different color and draw the trail we're walking on. Let's do it in blue. Here's the trail we're walking on. Maybe it comes like this and goes around and something like this. And then this is the trail that we're walking on. Okay? So this trail is our constraint. We're not looking for the maximum point on this mountain range, the highest elevation on the entire range. We're only looking where is the highest point we reach along this trail, right? Do you agree that in this picture, it's this point here? This is the highest point that we reach. Do you agree? Everybody? Okay. Now, what do we know? So these lines, these black lines, these are level curves of the form fxy equals some fixed number, some constant c. So here the constant is 100. All these points xy satisfy that the value of the elevation is 100. All these points satisfy that the elevation is 200, 300, 400, etc. And this blue line is not gxy, that was a typo. It's gxy equals 0. That's this line, that's this curve, right? It's all the points that satisfy gxy equals 0. Do you agree? What do we know about the gradient of a two-variable function? Hint, level curves. Exactly. The gradient of a two-variable function is always perpendicular to the level curve at every point. Okay? So at every point that I look at, the gradient is perpendicular to the level curve. Here, and here, and here. At every point, the gradient is perpendicular to the level curve. Do you agree? Okay, so this is the gradient of f. At this point, the gradient is perpendicular to the level curve at this point. Clear? Now, gxy equals 0 is a level curve of g, of the function g. G is also some two-variable function, and gxy equals 0 is a level curve of that function. So the gradient of g is also perpendicular to the level curve, to the 0 level curve of g. Here it is. This is the gradient of g. Do you agree? And that should be true at any point. Clear? The gradient is always perpendicular to the level curves. What's going to happen at this specific point? At this specific point, which is the point we're looking for, where the trail we're walking on, he never drew us walking on the trail, right? Here we are. We're walking on the trail. The highest elevation is at this point. At this point, the gradient of g is perpendicular to the level curve. Let's draw it a bit bigger so you can see. This is the gradient of g in blue. And the gradient of f in black at the same point is also perpendicular to the level curve at the same point. Do you agree? Everybody? So what can I say happens at this point? And it's unique for this point. It's not true for this point. Let's use the two of them. Here's the gradient of f in black. Here's the gradient of g in blue. At this point here, for example, here's the gradient of f. Here's the gradient of g. At this point here, there is no gradient of g because it's not on the trail. We're not interested in that point. At this point here, gradient of f, gradient of g. But at this point here, at the highest elevation, if you take the level curve that goes precisely through that point, this is the situation with the gradients. They're parallel. Do you see that? Okay, so at the point we're looking for, at the maximum point, the gradient of f is parallel to the gradient of g. Is everybody with me so far? And this is a unique phenomenon that happens at that point specifically. Does everybody see that? Good? Okay. Now, what does it mean? These are vectors, right? These are vectors. The gradient is a vector. Its components are the partials. What does it mean the two vectors are parallel? Two vectors being parallel, what does it mean? We called it, we had a different term for it. Remember what the word we used was? Collinear. Remember that word? So what does it mean for two vectors to be collinear? That one is a scalar multiple of the other. Remember that? So call that scalar. So these two are collinear, implies that the gradient of f equals some scalar. Suggest a name for that scalar. Lambda is a good choice, but I think the way we wrote it, it's going to be minus lambda. Yeah. Let's call that scalar minus lambda. Do you mind? Times the gradient of g. If they're parallel, then one is a scalar multiple of the other. Clear? So if lambda f equals minus lambda, that's what I chose to call that scalar, times lambda g, then the gradient of f plus lambda times the gradient of g is 0. So let's erase this level curve a bit. So therefore, the gradient of f plus lambda times the gradient of g equals 0, and that can be written as the gradient of f plus lambda g. The gradient is a linear function, vector function. Good? And that's the statement of the theorem. At this point, at the max. Is it clear? Is the intuition clear? Okay, so the idea is very, very simple. I'm assuming that this is what Lagrange or Euler had in mind when they were exploring these ideas. And that's the idea behind this. Okay, very geometric. The formal proof is a bit more formal. Questions about this? Everybody good? Okay, so what we didn't do is do examples using Lagrange multipliers. And that we're going to do in the next clip. Which is going to be